Thank you. So it's a pleasure being here. I'd like to thank the organizers for inviting me. So I changed the title of my talk from a complete classification of multipartite entanglement to the little we know about multipartite entanglement. It seems more kind of perhaps closer to the truth. So this, my talk is based on a paper that I wrote together with Nolan Wallach from UCSD. And what I'll start today is, I want to start with some notations that we use in quantum physics and quantum information. So it will be clear what we're talking about. I'll be using constantly this notation 0 to stand for 1, 0, a vector in C2, and this is the 1. And the dual vectors are, we denote them as by a bra. So this is called a bra and this is a ket. And any qubit, when we say qubit, what we mean a vector in C2 that we write like that. And typically it's normalized. The vector is normalized, where A, B are over the complex. Everything I'll talk about today is over the complex field. And of course the dual is looking like that. So this is the psi of Schrödinger. It's simply a vector. And this vector encodes information about the spin of a physical system or any other information. But we can think about it as spin. And the meaning of this 0 here can represent spin in the up direction, and 1 can represent spin in the down direction. And then this vector representing that there exists some measurement that I can do, and there is some probability to get up and some probability to get down, and there is ways to calculate those things. But I won't go into it in details. But what I will talk about is another notations that we're using, and we call it the partial trace. So we're looking at a vector in Cm tensor Cn, and any vector like that is Cm tensor Cn is isomorphic to m by n complex matrices. This is the matrix A. So I would like to define something that's called partial trace, that we're tracing out the system A. A represents here Alice. We're typically thinking we have two parties sharing a quantum system. Alice holds one system and Bob holds another system. The dimensions don't have to be the same. And then we define the partial trace. For example, if I'm tracing over Bob's system, what it does to this vector, it makes it into a matrix, and the matrix is called the reduced density matrix. It's a matrix just A star A, where A is not Alice. It's sorry, I realize I'm using A here. This A is this matrix here, Aij. So this is the density matrix. Now we're saying that a state, Shmuel today talked about entangled states. Entangled state is any state that is not product if it's a vector. So here we have this vector. I'll be talking only about vectors, rank 1 matrices. And a product is not entangled, but anything else is entangled. And a maximally entangled state is a state for which either the partial trace, either the reduced density matrix of Alice or the reduced density matrix of Bob is proportional to identity. Okay, so we're saying this is maximally entangled if either this or this is identity. Okay, so that's this is the terminology. I hope it will be clear. So now I want to, before going into classifying entanglement, I want to give you kind of a little bit of an overview on what we know about maximally entangled states, those type of states that I described before. But this time, suppose that we have several systems. I can think about them, the electrons. Electrons are not necessarily green, but for some reason I like to think about them as green. And they are entangled, so this circle here represents that they are somehow correlated. The information, because quantum state essentially encode information about the system. So a system with the number, we have here several qubits, and each qubit can be correlated with the other qubits. We say that a system is maximally a state is maximally entangled if, when I look at it as a bipartite card, so maybe I'll write down here what I mean. So I have a...
May I ask you why you call qubits? I don't...
Oh, why I'm working with qubit?
Qubit, sorry.
Yeah, qubit, okay. Quantum bit, because that's the building block of...
Not just my poor understanding, sorry, okay.
Yes, so let's think for simplicity on qubits. If it's not a qubit, if it's a three-dimensional, we call it qtrit, and after that we don't have names for every number, so we call it qdit, if it's higher than 3. And we're denoting, so suppose I have a system of several qubits, right? So I have several qubits, maybe n. And now we want to know what is a maximally entangled. So maximally entangled meaning that every qubit here is maximally entangled with the rest. What does it mean? It means that if I look at it like that, like a bipartite card, thinking about all of this as some Cn, then I have two systems, right? And then maximally entangled is just like I defined before. If the state of the system so if I have a state psi here belongs to here, I think about it in C2 tensor Cn, then I say that it's maximally entangled. If I trace out this system, and I get a density matrix that is proportional to the identity. Okay? So that's the definition.
You do both traces?
Now, both, of course, it's not the same dimension, so it can never be proportional to the identity. If I have more than... only one of them would be proportional. If I go backwards... The smaller one. Either, typically, if this is not the same dimension, one of them is only... Yeah. So, but maximally entangled, that's not enough. We also require that any two of the qubits satisfies the same story. Any three, also maximally entangled, and so on. So any bipartite card, the smaller one, will be proportional to the identity. This is the definition of a maximally entangled state, the way I define it here. And now the question is, do we have examples of such states? We do in 3 qubits. Maybe I'll ask you, anyone can think of which state in 3 qubits, in C2, tensor C2, tensor C2. And so what we are looking for is the state in this system that if I trace out any 2, I get maximally entangled. And so it's actually the state that we write is called the GHZ state for reasons in physics that we have. It has been used to show that quantum physics predict certain things that we can't predict in classical physics. That it's fundamentally different. But for us, we're going to look at it. What does this state mean? Perhaps in notations, I should also mention that whenever we denote 0, 0, what we mean by that is just, right, 0 corresponds to 1, 0, and then tensor just 1, 0. So it's just a short notation for this, okay? So this is the notations I'll be using here. So if I have 3, it's just another tensor. So this state, one can see that if you trace out any 2 qubits, you get something proportional to the identity. What about 4 qubits? It doesn't exist. There is no such state that if you trace out. The reason, because if I have 4 qubits, well, it's hard to see the reason exactly, but if we have 4 qubits, the requirement is not just that every one is maximally entangled, but also every bipartite card should be maximally entangled. So it's C2 tensor C2 tensor C2 tensor C2. So we want also bipartite card like that, which is 4 by 4, to be maximally entangled. So it doesn't exist. There is no such state. But in 5 qubits, it does exist. And it's unique. There exists only one such state. It is written here like that. It's used, this type of states has lots of very nice properties, and it's used in error correcting code. It's called the 5-qubit code state because it's, we can use it to correct one qubit, one error. And the way we define it, here it's 0, 0, 0, 0. It's just, again, it's E sub 0. It's the standard basis tensor itself. This bracket here corresponds to cyclic permutation, so adding. It's just because I didn't want to write a very long state. It just means 1, 1, 0, 0, 0 plus 0, 1, 1, 0, 0 plus. Like the 1, 1 just got, so there are 5 terms here. It's cyclic, 5 terms in each of those, and it has to be normalized, so I divide by 4. This state is the unique. What I mean by unique, of course, unique, I mean up to local unitaries. So if I apply an element of SU2 times SU2, or not SU, I mean it can be U. So up to an element like that 5 times. Up to local, this is what we call local unitaries. Up to an element like that, this state is unique. Yes? Yeah, but it's, you can do the permutation, but you can achieve it by local unitary. So everything that you can get is up to local unitary.
So, so this is not a generic tensor in that sense?
No, this state is...
So you're saying if you take a generic tensor, it does not have this property, but your tensor does?
Yeah.
So this is a polynomial condition, it looks like. That's confusing. I mean, you're asking about non-vanishing of polynomial.
No, that's actually if it's an, if we will, I'll talk about polynomials in a second, but this state actually give you a maximum on your polynomial. Not only that it's not vanished typically.
Because you only have conjugation, you don't have left and right action.
Yeah.
Oh, okay, now I understand. Yeah.
Now I understand, because I thought you had left and right action, but you only have conjugation.
Yeah.
So generic will have distinct eigenvalues, whereas multiple the identity is special. Yeah.
Okay.
Okay. Now I understand.
So now what about 6? Also exists only one, and it's being, we can build it from this state actually. So up to local unitary, it's also known to exist. And again, when I say it's unique, every time I say unique, it's up to local unitary. So it's unique, and we can build it like that. We're taking this one, and then the knot of this, which is just everywhere I see 0, I put 1, everywhere I see 1, I put 0. On this state, I put it here, and look at tensor product like that. That's also unique.
Do you have kind of a geometric description of this state? So let me say what I mean by that. So let's take the U2 to the 5th orbit closure of that state, right? That's some algebraic variety
Right.
inside our space tensors. Do you have a description of that variety other than as this orbit closure, or at least the dimension of it? I mean, what's
Yeah,
the
it's very, very high. That's the...
well, it can't be that. It's not that high. I mean,
but I mean, it's very quickly. What I meant is the more you increase the number of qubits in general, it goes exponentially high. So that particular, I don't know.
No, but you're just adding a copy of U2 with each dimension you add, so the dimension can grow at most by whatever, 3 or 2 each time.
So I guess so what's again the? I'm talking the dimensions, the orbits under under U2.
Yeah.
You're looking at the orbits under U2.
Well, you're only interested in this up to the 5 copy. Let's just stick to 5 qubits. You're only interested in it up to the action of U2 to the 5th, right?
Yes.
So I'm saying, let's take the U2 to the 5th orbit closure of this to get a geometric object.
Right.
Can you identify that geometric object in some way other than as the orbit closure of this?
Maybe let's reformulate it like this. Let's say I give you a state and I ask you, is this maximally entangled, right? So this would mean that you would need to identify that it lies in the orbit of that, right? Is there some way that you know of identifying whether it is or it is not in the orbit closure of this state?
Equations.
Yeah, the equations, the way I will do it, I'm not sure, but I'll say that the way I understand it, if you give me a state, I have a very simple way to test if it's on that or not. There is the equation. I'm just tracing out any number of qubits and I check. And in fact, it's enough to check tracing out the bigger sets. So like I can look here on all 2, like say in 4 qubits, I will look at all 2 versus 2. So there are 3 options. And I check if this trace is identity or not. And
But you said that does not exist before. So
no, exactly. This one doesn't exist. So in the 4, it would be any 2, 3. In the 6, it will be only 3, 3. I don't need to go on the smaller ones because if the bigger ones are satisfied, are proportional to identity, obviously the lower ones. But I don't know if that wasn't the question, I guess.
Those are equations.
No, I know what the equations are. It's just the projection onto the trace list is 0, but...
You want to know the dimension or what?
The dimension, but for example, the first one...
The dimension of the orbit.
For example.
Yeah.
What's the isotropy? I mean, is that
Yeah,
fixed
yeah,
by
yeah.
anything?
Would you be interested?
I don't know.
So for the GKZ state, there is the hyperdeterminant that's going to tell you whether it's entangled or not.
Yeah, the hyperdeterminant will tell you typically what is generic, like generic entanglement. Yeah, it will typically tell you which, but there are many measures. The hyperdeterminant can be 0, but the state's still entangled.
I see. Okay.
Yeah.
Do you know if it's the orbit of a weight state in that representation, and if so, which weight?
That's kind of...
It's not the highest weight, because that's unentangled.
Yeah, that's kind of description. I was hoping for something like that.
Yeah, I don't know. Yeah, on that one. In fact, what I would be interested is actually in the SL orbits, not so much the SU, because the SU is, as we will see, is more. SU is much more complex, I will say, to classify all the SL orbits than the SL. So, I mean the SU than the SL. Okay, so as I said, 6 qubits. In 7 qubits, we don't know. The answer is that we don't know if such a state exists. And Eric Rains showed that for bigger than 7, it does not exist. So this is kind of just to give us a picture of what's going on just in terms of maximally entangled states. So what I'd like to do now is to talk about what we know in how do we classify entanglement. So this was just maximally entangled states. Now I want to discuss how we classify entanglement in quantum information. And typically there is a set of operations that's called local operations and classical communications, or we call it in short LOCC, which is a very restrictive type of operation that tells you what you can do if you want to convert a state to another state, or a system, what you can do to a system. And it turns out that a better way to study entanglement is to look what we can do under stochastic operations, which means I can convert one state to another state at some probability. So there is some probability, non-zero probability, that I can convert one to another, and that is called SLOCC. So it's basically local operations, but it's not enough that they are local. they are also not deterministic ones.
Can you explain a little bit more?
Yeah.
Just mathematics.
So what do we think? What is entanglement? I'll go by entanglement. Entanglement means global correlation, right? So it's some sort of correlation, but it's not classical correlation, right? So the way we define entanglement is by what cannot generate it. What cannot generate entanglement? Local operations cannot generate entanglement because they are not global. Also, classical communication cannot generate entanglement because it's not quantum. So anything that under local operation and classical communication, this is LOCC, that is monotonic under those transformation, local operation and classical communication, I cannot increase the entanglement. So any measure of entanglement is a monotone under LOCC.
Is this a fact about entanglement or a definition?
That's a definition. Entanglement is a property of a physical system that you cannot increase under LOCC. And mathematically,
What do you do for just I want
yeah, so mathematically, yeah, this is, by the way, still the, this is just a review. I'm far off from,
Okay, it's up to you.
yeah, but I'll just say one thing about it. So typically we're thinking about, I will be talking about pure entanglement, which is described by vectors in Cn, right? So the space that I will be looking at is SCM1, tensor CM2, and so on, tensor CMN. This is the space I will be looking at. However, and I'll be looking only at rank 1 matrices. Typically, a physical system, the information about the physical system is encoded not in a vector but actually in a matrix, which we denote rho, that is, if this is H, if I call this, this is our Hilbert space, which in this case is just a vector space, it goes from H to another H. Okay, so here it will be the same H for now. So this is a density matrix. Okay, it's a positive semi-definite Hermitian matrix that has trace 1. Now, what is LOCC? LOCC, I go to the lab and I do something to the system, but I do it locally. So LOCC is a completely positive map acting on this, which we denote sometimes by this epsilon, which is applying this completely positive map to rho. I get another density matrix, let's call it sigma. Now LOCC, any completely positive map has a representation as a sum m sub k rho m sub k star. I can write where m is some any complex matrix. This is all matrices here. And I sum it over the k. So any completely positive map has this structure. And if it's LOCC, then this structure, mk, for us, for now, is ak tensor some bk on system. That's the bipartite case. So suppose we have only 2 for now. So the A is a matrix acting on this space, and the B is any complex matrix acting on this space. And any allowed operation has this form. That's essentially what is LOCC. For us, not quite true. This is called separable state. LOCC is shown not to be exactly that, but I have to define it operationally. So Alice does a measurement, send the result to Bob. Bob perform based on the outcome of the measurement, but that most mathematician won't understand that kind of definition. So I think this is the closest I can come to LOCC. But that's too restrictive, so that's not what I'm going to talk about. I'm going to talk about something which is, has some probability. So instead of achieving this with certainty, this represents achieving it with certainty. If I take off this, the sum, this is, I can achieve each element here with some probability. And that's what we will consider. That's why the group that will be involved in the characterization of entanglement would be SL. So the group I'll be looking at is the SL And for qubits, it will be 2c tensor n times, depending if we have n qubits. I'll be looking at that. That comes from physics, from the fact that I don't want to be able to increase entanglement under local operations. So if I apply an element of this group to the vectors that I'm writing here, in principle, I cannot increase the entanglement. So that's what really classifies entanglement. I know this is, there is a lot more to it. It's kind of in a nutshell.
But is this an honest definition now of how you apply this group? And
yeah, so now for us, this is it's essentially to classify the orbits under this group. Every orbit is an entangled state that has nothing to do with another orbit. Like the entanglement is just different that you cannot even compare. So entanglement is not like one quantity. It's actually a whole classification.
But you have a partial order on entanglement.
Yes, exactly. It's a partial order. Exactly. So this is what we have. This is for 3 qubits. So let's look what we have in 3 qubits if I look at SL at this group. So on 3 qubits, I'm looking at this group and I want to classify it into its orbits. And so I wrote down two types of states, the W and the GHZ. This is under this orbit. Those are the ones that we will say genuinely entangled. These ones, there are other orbits where you can see this is some state between Alice and Bob, the first 2 qubits, and the third qubit is completely, it's a tensor product here, right? So we just don't write tensor. This is completely disentangled from this state. So those 2 states are completely, these systems are completely not entangled. That's why these kinds I put here in the lower hierarchy of entanglement. And this is the most non-entangled state because in every bipartite card there is no entanglement in this state. And you can see that this doesn't generate entanglement. You cannot go from here higher. So this is the lowest entanglement, this is the middle, and those are the most entangled. But this one, in some sense, is the generic one. Actually, in 3 qubits, the rank 2 is the generic, not the rank 3. That's what it turns out. So this is the generic one. So it's a dense, this is an open dense set in the space of 3 qubits. Okay, so this is what we know about 3 qubits 15 years ago, almost.
Just one second. With GW, what would be the orbit of GW?
It's the tangential variety of the sig, right?
Yeah, so by the way, to everyone who don't know it, I'm a physicist, not a mathematician. So be aware of that.
So it's the set of all tensors, 2 by 2 by 2 tensors with hyperdeterminant 0. That's how I would describe GW. Is that right? Okay.
Yeah, I wouldn't think about it in this way, but it's true, I guess, in this case.
Well, that being said, is everything that orbit and below, right? That's the closure.
Oh, yes. Yeah,
I already talked in my talk, so.
Yeah, he will be talking about hyperdeterminants and entanglement.
Okay, so let's move on a little bit. So now I want to talk about how we're classifying it. So we will be using the Kempfness theorem. And what I write here is, sorry, again, the tensor here is just an X, okay? So there is no circle, no need for a circle here. It's just a typo. So we're looking at this group, we're looking at this space, and what I did right here is the Kempfness theorem for my purposes, okay? So of course you can write the Kempfness theorem more general. So in this case, we're looking at n qubits. This group, this is the local unitary group that I'll be looking at, the Lie algebra of this group, and we define a set of critical states. Those critical states, those are states that satisfies this relation. Now, in physics, this is an inner product, so it's x applying to phi, and then the inner product of that with phi. Okay?
So this is for all x.
Yeah, for all x. Oh, I forgot. Yeah, for all. Yeah. For all x in G. So then writing it in this group, in the group picture, it tells us that it has the lowest norm, that those critical states has the lowest norm, and the perhaps non-trivial part of this Kempf-Nest theorem is this. The third part is that G phi is closed if and only if G phi is in the intersection is not empty. Okay. Now so these are the sets of critical states. Now, how these states related to entanglement and why this is important to us? The reason is because every element of critical state is critical if and only if, when I look at the bipartite cut between this vector and the rest of the system, is maximally entangled. But only one, not two, like I did two. And we can see it very simply by, just to get intuition where it's coming from, just suppose that I have this qubit and it's maximally entangled with the rest. It means I can write it like that, where phi 0 and phi 1 are orthogonal states. So phi 0 and phi 1 are just elements of n minus 1 qubits. Okay, so it's a big, it's a vector in a, it's not in dimension 2. Okay, so we're looking at C2 tensor, and then we have C2 tensor C2, and then I'm looking at it like that. So this is, so phi 0 and phi 1 are orthogonal states belonging to here, okay? So these states belongs here, and this is the first one. So if we're looking at the first qubit, to get the intuition where it comes from, you can see that if it's maximally entangled, I can write it like that, where these are two orthogonal, and then you can easily check that if you apply these three Pauli matrices on the first qubit here, and you do this inner product between this and this state, you get 0. And
maximally entangled is an extremely pathological condition.
yeah.
Yeah, it's strange.
But this is not maximally entangled completely. Okay, this is not just notice the difference between, this is not maximally entangled, this is just, every qubit is maximally entangled with the rest, but not.
Already that's very pathological.
Yeah.
But physics is about special stuff.
But that's, yeah, exactly. In physics, yeah. The interest, yeah, exactly. The most interesting states, like we've seen before, are actually those that are very special. They are very non-generic. They are highly non-generic, let's say, in this way. And in fact, it's even, yeah. Okay. So let's look at the example of 4 qubits. So to understand these critical states, the 4 qubits, again, sorry for the typos here, there should be a line here. And again, ignore the circle. We have we have this group, we have this local group, and then the set of critical states can be characterized very nicely. In 4 qubits, it turns out that you can characterize it in terms of a 4-dimensional vector space, where up to local unitaries, we can write it like that, where the I should define what are these states. So what is psi plus, psi plus? So psi plus minus is 0, 0, plus minus 1, 1, and the phi plus minus, oh, maybe I'm wrong, one second, this is 0, 1. Typically in quantum information, these are the notations, and this is a 0, 0 plus minus 1, 1. Okay, so these are the those are the vectors, and what you can see is that every critical state up to local unitary looks like that, where we have this 4-dimensional space spanned by those 4 vectors. Okay, so this is a very nice picture. It also tells us that most of the states are in the orbit of A, where G is this SL. So most of the states here. And in some sense, in every orbit, under the SL, the critical state is the maximally entangled state in that orbit. Everything else, in some sense, is less entangled because it doesn't have, because it's not critical and it doesn't have all these nice properties. Okay.
So can I ask you a question?
And I'll skip this. Yeah.
Can you help us out just with the numerology? So in this case, we have a 16-dimensional vector space, 12-dimensional group, and you have a 4-dimensional vector space that you move around that gives you almost everything.
Yes.
Is that what you expect in the n qubit case?
Yes. Always, it's always true that the critical set, if you look at the orbit of the critical set under the SL, it's always dense.
In the same numerology, we have a 3n-dimensional group, a 2n-dimensional
Yes, yeah.
space, and the difference in the dimensions is...
Yeah, and there are more states though that are interesting. There are states in the null cone. I'll talk if I'll get the time. I'll talk about it. And there are many other states that are actually not here that are also interesting. In for example, in the W state that I wrote down, it wasn't critical and. But what it tells us that there are that there are many. This also implies essentially that the SL invariant polynomials. There are 4 independent SL invariant polynomials, basically. Okay, I'll skip this because I think I'm out. How much time do I have left?
13 minutes.
Oh my gosh. Okay. So let me define. So our goal, what I would like to do is to show you how we can actually classify all entangled states according to to classify all the orbits under SL, the SL group. And we're looking to do that. We're defining SL invariant polynomials, which are, for simplicity, I'm assuming the dimension is 2, but it doesn't have to be there. It can be any dimension, and they don't have all to be the same. But for simplicity right now of the exposition here, I assume this. Then any function that is SL invariant is called SL invariant if it's SL invariant. The function f goes from Hn to C here. Everything is over the complex. Now, this is for the physicists, so none of them are here, so I'll skip it, but there are examples how we define SL invariant. Basically, this sigma y, maybe I should write it. This sigma y is this. So define the antisymmetric matrix J. Let's call it J is the analog of sigma y, 0, 1, minus 1, 0. I look at this, and so an example of an SL invariant polynomial is J tensor J applied to psi, and here I put the bar in the basis where J looks like that, okay? So I'm taking the bar here meaning, so it's the dual, but then I do bar on this, so I'm taking the complex conjugation away, okay?
It has to because it's SL.
Yeah, because it has to be, it's a bilinear form, So this is, and so that's an example, and it's unique. For 2 qubits, there's only one SL invariant. For 3 qubits, there is also one. It's the Cayley hyperdeterminant, and it can be written like that in terms of the 2. If you break it like that, if you take a state in 3 qubits, so this is a 2-qubit state, I write it like that, not necessarily normalized here.
But
and
for the mathematicians, you just quote fundamental theorems of invariant theory, and we know what these things are.
Yeah. Okay. So, and then we can go on, and there is more examples. And also there is something useful I will skip. I'm out of time. And let's go to distinguishing all the SLO orbit. And let's be now, I'll start now. So just now I'm starting my talk. I should have started from here because now I want to talk about the general case. So we have n qubits. And first of all, I want to show you that actually SL invariant polynomials are not so good for us to distinguishing the orbits, because in physics, we're only interested in normalized states. So suppose that I have one state. This is an element of its orbit, But the state that I want to compare it with is a state that is normalized, and it might be different up to some phase. So this is really what we want to look. So I'll say that this state phi and this state psi are in the same orbit, in the same physical orbit. Not mathematically, this is what it means. So because we have this factor here, SL invariant polynomials, you know, if I take, say, you take an SL invariant polynomial of degree k, we have this factor here coming out. So SL invariant polynomials by themselves cannot distinguish the polynomials for us. So what do? We're looking at the ratios, of course. So it can be shown that the ratio between two SL invariant polynomials of course, that if they are in the same orbit, this is obvious, and the other way around, you have to be careful. First, we assume that there exists a SL invariant polynomial that is non-zero, and if this is satisfied, then we can then it follows that the states are in the same orbit.
It assumes that they're the same degree, right?
Yes, the same degree. Two homogeneous polynomial. The k here is presented degree. So if this is hold for all k, for which hk is for any k, so whenever this is possible, when it makes sense, I hope, from the context. Okay, so the next thing is what are the degree? What are the possible degrees of the SL invariant polynomial? So now I convinced us that in order to actually SL invariant polynomials are good even for this, because all we're doing is looking at the ratios instead of the actual. So they are good to distinguish the physical SLOCC classes of states. The next thing is what the possible degrees of these polynomials. So that's simple. If I take, this is an element of the dimension, right? H was CM1, CM2, CM up tensor CMN. So this is an element, implies that, so if I take an element so if I'm looking at a state and I want to calculate what it's, suppose I have a polynomial of degree k, then because this, if this is a root of unity that satisfies this relation, it implies that it's in G. And because this is SL invariant polynomials, we have this relation. But then I can take it outside because it's homogeneous of degree k, so we obviously get condition on what the dimension of the SL invariant polynomials could be, and they have to be the LCM of the different local dimensions. Okay, so that's the dimension. Now, how do we find all of them? And the main idea of how to find all the SL invariant polynomials, it seems like it's very hard because they're growing, their number grows exponentially with the number of qubits and the number of and the dimensions, the local dimensions. So it seems to be a very difficult task, and that's why we, for a long time, people found only the SL invariant polynomials of 4 qubits, but that's where it stopped. We couldn't go much beyond. There are some hyperdeterminants, some example of SL invariant polynomials, but not finding all of them. And our idea here is, the main idea is, rather than looking at all the SL invariant polynomials at once, we're just going to look at just to fix the degree and find all the SL invariant polynomials in a fixed degree. And that's remarkably simplifying things a lot. So that's the main, essentially the main idea. Rather than fixing n, we're going to fix k. K would be fixed. And then if we then we can define so any so now any SL invariant polynomial of degree k, I can write it like that, and inner product here tensor prime states, and v is in here, and then because it is SL invariant polynomial, we require that when I apply G, an element of this G here, if I apply it k times, in the natural way, essentially, on V, then it fixes V. So this is the standard way. to do these sorts of things. And so we have an SL invariant polynomial of degree k, which is G invariant. And essentially, therefore, what we are interested in is finding all the fixed point of this space. Okay? Is it clear? So how we do that? The main idea is, because the G here is a tensor product, and we have K, is an intertwining map, which is a trivial observation. It's just, if we're taking K copies of this Hn, it's equivalent of taking K copies of each one of them separately. And so if, I have here this nice picture, I'm very proud of that picture. It's because I tried to find a picture for this. The green is, the blue and the red are different dimensions. So suppose we have H3 of 3 quantum systems in different dimensions, and I have 4 copies, so I'm interested in degree 4 polynomials. And what we are just doing is just looking, instead of looking at it like that, we're looking at it as 3 copies of the same dimensions here. And what this does, in short, is it's reduced the problem. Instead of finding the fixed vectors of this space, all we have to do is finding the fixed vectors of this space. And that is much simpler problem. It's actually...
Why is that true?
Why is that true?
That gives you a complete list. Some of these may map to 0.
No, but I mean, you might imagine you have a fixed thing here, which is not a tensor of fixed things. Like,
yeah, because... yeah, so
you could get...
what it does is
0, but you get a complete list.
That will take care of this. Just keep going.
Okay, maybe I'll ask you.
What?
Just keep going.
Okay, I'll keep going. Okay, I'm going. Okay, so to summarize, essentially what we showed is that the fixed points of this are equivalent to this. And so all we need is to find this, and for this we have the Schur-Weyl duality that tells us how to find the projection to this, essentially, and it's given like that. The sum is over all the permutations, the permutation group over k elements, and this is the character of the partition of lambda is given here, because the point is, if you remember what I told before, is that the degree k must be divisible by m. Right? It has to be divisible by each one of those m's, and that's why we can write k like that. So we're looking at this partition, and d lambda is the dimension. So we have this, and so that's how it's. So essentially, we found out all SL invariant polynomials of a fixed given degree. Okay. The problem is, of course, what we don't know is when to stop. So if you go in degree 4, say in qubits, they all have to be divisible by 2. So it's degree 4, degree 6, degree 8, degree 10. That's where we don't know. We also did some calculations on the dimensions. We have the number of SL invariant polynomials of degree 2. For n qubits is this. For 4 is this. For 6, degree 6 is this. In 5 qubits, you can check there is only one SL invariant polynomial of degree 6. And we found it, actually, just for fun. And then there are degrees 10, and we have some nice program that actually can, really up to if we put here 100, it gives it in Mathematica. I just produce it in a few seconds. So it's very nice, but the bad news is, of course, this is exponentially both in n and k. So I mean. And we knew it ahead of time, but we can't expect to find. But at least we identified them all. So they all related in this way. Now I have a lot more to say. What's the time? Oh, it's the end of the time. So I'll just say that there are there are simple constructions that we also found. And I'm not going to say there are some monogamy of entanglement. There is a lot more. I mostly gave you a review today. But I'll just summarize that essentially SL invariant polynomials can we call them slips. They can be used to classify multipartite entanglement. That was when I talk about the ratio, because that was very important for a physicist. Because we needed to look at the ratio. That's really the quantity that a physicist would be interested in, is what is the ratio between SL invariant polynomials, not their value itself. They essentially it can be for a given degree. We can compute them using essentially the characters. The number of slips goes exponentially. They also have they play an important role in something called monogamy of entanglement. It's a property that if you have like three parties, like Alice, Bob, and Charlie, then if Charlie is very highly entangled with Bob, then it has to be not highly entangled with Ali. I got confused with the names, but you understand. Yeah, it's good. I'm monogamy guy. Yeah. Then critical entanglement decay quickly under local noise. I didn't talk about it. I didn't talk about majorization and partial order, which I didn't have time. Yeah, so I'll stop here. Thank you.
Questions?
Yeah. For your first bullet point here, is it possible that you have two different orbits that both have all the same values for all of the SL invariant polynomials that you cannot distinguish with just invariance polynomials, and maybe you need something more?
Yeah, like for example, if you are in the null cone, so the null cone is defined as the space that all the SL invariant polynomials are 0. So this won't tell you anything about that. So it doesn't contain everything. And there is some even orbits that we call them, they are not stable, that they are kind of a linear combination of So if I have two vectors and I look at this, so this one is in the null cone and this is not in the null cone. So they also, what I said is not going to help you in that case. So essentially, what I talked about is in critical state, it distinguishes the orbits of the critical orbits. Orbits that has a critical state. They don't fully distinguish everything. Yeah. But they can still. I mean, if a state is not critical, so if this is critical, but this is not, this is in the null cone, then it will still tell you some things about this guy. Yeah. Don't know if that makes sense.
So you can use to help classify, but maybe not completely classify.
Yes.
The
Yeah.
usual GIT that you have some orbits that can be distinguished by invariance and some that can't. Unstable, semi-stable, stable ones.
Yeah.
There's questions over there.
Oh, yeah.
Yeah, I just wanted to hear more about this Nielsen law. I don't know, is it related? Have you seen this?
Yeah.
thing
So
that back in about
if I'll, yeah. So the Nielsen, it's here. It knows that if we have two bipartite states, so this is, we're talking about two systems, Cn tensor Cm. If I have Cn tensor Cm, so I'm looking at vectors here. And it turns out that the LOCC relation is equivalent, so I can go from here to here by LOCC if and only if there exist probabilities Pi and unitaries, and some set of unitaries, any unitaries, matrices, that such that the reduced density matrix, what I talked about tracing, the partial trace. I trace the B here and I trace the B here, so I compare between the reduced density matrices of this. If they are related like that, then I can go from here to here, and it's if and only if. And it's also known that two Hermitian matrices are related like that if and only if the eigenvalues of rho A are majorized by the eigenvalues of sigma A. Now in the multiparty systems, it's very hard to do that, but we define something analog to that. And I won't go into details, but I'll just say that one can go from psi1 to psi2 by separable operation, which is very similar to LOCC, a little bit bigger set than this one, if and only if there exist unitaries that are in the stabilizer of this vector psi. So there is some analogy that implies majorization, but not backwards. You cannot go backwards. So it's a more restrictive condition. But that's about it. Yeah, I can talk about it in more details. Guess after. Yeah.
I just have a comment, which is this fact that classifying these critical orbits up to SU is the same as classifying all orbits up to SL. That has a name in the mathematics literature. It's the equivalence of a complex GIT quotient and a symplectic quotient that zeros at the moment. Just in case you didn't know.
Yeah. And I mean, in the orbits, I didn't mention it, but it's true that in the critical set, if we're looking at SU orbits versus whatever you can do with SL, you can do. If you can do some transformation with SL, you can do it with the SU if the state is critical.
That's this fact which I was.
Yeah, I actually didn't know its name, but I knew of it, yeah.
Thank you again.